In this presentation, we're looking at stability again. We're going to start with a brief overview of the stability conditions we've studied so far, and then we're going to study the stability of systems which are not written in the standard differential equation form. First, we'll do the stability overview, and that's summarized here. Now, for this, I'm assuming a standard form for our system description. So the system here is linear, time invariant, and continuous time, and is written either as a differential equation or as a convolution relationship. So you're either given the differential equation system description, which would be q of d times y of t equals p of d times x of t, or you're given the form y of t equals h of t convolved with x of t. So on this page I've got various conditions which we wish to establish for our system, and the checks by which we establish them, and also what is implied by the condition. So for example, if we wish to check asymptotic stability, we need to see if all roots of q of s are in the left half plane. And if we have asymptotic stability, that of course implies Bibo stability. Results are summarized here for asymptotic stability, Bibo stability, Bibo instability, asymptotic instability, and marginal instability. Nothing is really new on this page. I'm providing it just so that we can have all of our stability results in one place. Now let's turn to the second topic of this presentation, and that is systems that are not in standard form. How do we analyze their stability? So the motivation here is sometimes we get a system description that's not in one of the forms that's covered by the previous page. The system is linear, time invariant, and continuous time, but it cannot be written as q of d times y of t equals p of d times x of t, or y of t is h of t convolved with x of t, or the transfer function description y of s equals h of s times x of s. So we wish to find the stability of systems that are not in one of these forms. To determine the stability of a system that's not in standard form, the easiest way may be to try to convert it to a system that is in standard form, or a combination of systems that is in standard form. To illustrate the thought process, let's consider some examples. Our first example is a relatively simple one. We have the equation y dot of t plus y of t equals x of t minus cap t. How do we analyze the stability of this system? The first thing to realize is that x of t minus cap t is just a delayed version of x of t. So we can block diagram it as shown in the middle of the page. We have x of t coming into a system that delays it by cap t. That gives us x1 of t, which is equal to x of t minus cap t. That then goes into a transfer function. This transfer function can be found by Laplace transforming equation number 1 and replacing the x of t minus cap t by x1. Then we'll find out the relationship between y of s and x1 of s is 1 over s plus 1. Now, if we look at these two different blocks, we'll notice the 1 over s plus 1 block is bounded input, bounded output stable because it has its pole in the left half plane. The delay system is also bounded input, bounded output stable because any input is just delayed. So if there's a bound on the input, there's got to be a bound on the output of that delay block. So since a bounded x produces a bounded x1 and a bounded x1 produces a bounded y, we know that any bounded input x of t will produce a bounded output y of t, and therefore the system is Bibo stable. Now let's look at our second example, and it is y dot plus y of t plus integral from 0 to t of y of tau d tau equals x of t. This is not in standard form due to the integral term. If we take a derivative of both sides, however, the integral term just becomes y of t. Then the differential equation is y double dot plus y dot plus y equals x dot. This is now in standard form, with q of s equals s squared plus s plus 1 and p of s equals s. All roots of q of s are in the left half plane, and so we have asymptotic stability. And since we have asymptotic stability, we also have Bibot stability. Our third example is the equation y dot of t plus y of t equals g of t convolved with x of t, where g of t is given by the graph shown. This equation is not in standard form due to the convolution that's occurring on the right-hand side of the equation. We'll convert it to standard form in the following fashion. We'll define signal z of t as the convolution of g of t and x of t, and then our differential equation is y dot plus y equals z, which is in standard form. So we can write our system as two equations. The first one is y dot plus y equals z, and the second one is z is the convolution of g and x. Let's look at the second one. Let's suppose x of t is a bounded signal. Since the integral from minus infinity to infinity of the absolute value of g is equal to 1, and that is less than infinity, we know that the output, z of t, must also be a bounded signal. If we look at our first equation, we'll find the transfer function is y of s equals 1 over s plus 1 times z of s. And since the transfer function is bounded input, bounded output stable, we know that any bounded input z will produce a bounded output y. That means that a bounded input signal x will produce a bounded signal z, and a bounded signal z will produce a bounded signal y, and therefore any bounded x will produce a bounded y. That means the system must be Bibot stable. This idea can be expressed in block diagram form as shown here. We have x of t entering into a system, and that system does a convolution of x with g and produces z. And then z goes in the transfer function 1 over s plus 1 to produce y. A bounded x will produce a bounded z, and then a bounded z will produce a bounded y. So that means every bounded x must produce a bounded y. I hope through these examples you see how you can handle some system descriptions that are in non-standard form. The best strategy to employ, whenever possible, is to convert the parts of the system, or the system as a whole, into standard form, and then to employ reasoning to deduce the behavior of the output.